Hi, my name is Alexa Vitti, and this is lab number 2 for Physics 2211. So the purpose of this lab was to observe the motion of an object falling from rest using computational models to evaluate the effect of drag force. So some fundamental principles in this lab include Newton's second law, which states that F net is equal to ma, which is equal to the change in momentum with respect to time, and the velocity update formula, which says that the final velocity is equal to the initial velocity plus F net over m, which is also acceleration, times the change in time. And then the position update formula, which says that the final position is equal to the initial position plus the average velocity times the change in time. So, summary of the result of the lab is that our second computational model, which includes both the force of gravity and the drag force, better models the data from the falling object. So for this experiment, we dropped a paper ball from rest, and then we analyzed the motion of it using Tracker, and then we created 2 computational models for the paper ball using GlowScript. So for one, we only took into account gravity, and then for the second one, we took into account both gravity and drag force. And then finally, we compared the models and determined which one fits the data better. So the initial conditions of the experiment were the position was negative 3.8, negative 3.8, 0, and then the initial velocity was 0 in all directions. And then the initial force was negative 9.8 newtons pointing down, which is the force of gravity, and then also the drag force, which is unknown, but we use the model of negative b v squared times v hat. So here is the experimental data that we obtained from Tracker. So as you can see, the mass was dropped. This is a position versus time. So as you can see, it started to terminate, the velocity started to terminate over the course of the time that it was dropped. So for the first GlowScript code, which did not take into account drag force, we set b equal to 0, and F net was just equal to the force of gravity. And then here are the graphs that computational model produced. So as you can see, the velocity versus time is just a linear straight line pointing down, which means that the acceleration versus time is just a constant value, which is equal to the force of gravity. So then, for the GlowScript code, including the drag force and the gravity, we set b equal to 0.004, which is an approximation, and then we accounted for this in the net force when we added it to the force of gravity. And then here are the graphs that computational model produced. So we have the position versus time and the velocity versus time. So for the velocity versus time, as you can see, it does start to flatten out towards the end, which we'll talk about why later. So then here's the comparison of the 2 models compared to the actual data. And as you can see, the second model, which takes into account gravity and drag force, better models the actual data. So some observations include that the computational model that accounts for both gravity and drag force better models the experimental data, like I said, and then the object starts accelerating at a certain point in its motion, which is known as the terminal velocity, which occurs when there is a drag force equal to the force of gravity. So some sources of error in the experiment include human error, video angle inequality, and then also other forces in the surroundings that are not gravity and drag that we did not account for in our computational models. So what do these results mean? So computational model 2, which includes gravity and drag force, predicts an eventual terminal velocity. And terminal velocity occurs when the magnitude of drag force pushing up on the object is equal to the gravity pushing down. So at terminal velocity, F naught equals 0, so therefore there is no more acceleration. So what if the object was thrown down instead of dropped from rest? So if it was thrown down, it would reach the terminal velocity quicker. However, the magnitude of the terminal velocity would still be the same, and we can check this claim by substituting our initial velocity in our GlowScript code for a value that isn't 0. So here you can see that here is the one that it was dropped from rest, and then here is the one that it was thrown down. And as you can see, this one starts to level out around 0.4 seconds, while this one starts to level out around 0.6 seconds. So, however, the magnitude of the terminal velocity is still the same. Thank you.